All right, hey everyone. So today I'm going to be explaining how to do the last problem, problem 3, on exam prep worksheet 9. So this problem is about a word search. So it's giving us an n by n word search and n words to look for. And our job is to make an algorithm that solves a word search in O of n cubed time. Okay. So immediately what that, when I'm doing this problem, what that tells me is that, okay, O of n cubed time, I have n by n word search, so n squared letters. So if I was to sort of do this linearly, right, just like kind of go through the entire word search and sort of deal with each letter at a time, that tells me that, okay, if I have n squared letters and I'm allowed to do n cubed work, that means that I can do n work for each letter, right? So if I visit each letter, I can do up to n work and still be within our runtime constraint, right? So that's maybe the first clue that you might pick up just by reading this problem on like an exam or something. Okay, so each word is at most n letters, okay? And for simplicity, no words contained within another, which means basically that words aren't going to be nested, right? So if we have a word, that's going to be a unique word in that path. There's not going to be anything else inside of that word. Okay, and then let's see. So we're also given a hint, which is that we can add the words to a trie, and that the longest prefix of operation might be helpful. Longest prefix of, which from here on out, I'm going to sort of abbreviate as LPO, takes in a string key, so say key, and it returns the longest prefix of that string in the trie. So let's take a look at an example of how we might use this. So let's scroll down here. So here I have an example trie, right? It has the words hi, which is right here. It has, oh, there should be there we go. That should be there. It has hey, it has help, and it has hello. This might be a little messy. You can maybe pause the recording and take a look at all those words. Let me erase this. Okay. So we have an example trie here, and then we also have an example word search on the right, which we'll use later on. But just to demonstrate what LPO does, let's say we call LPO, which is again longest prefix of, on the string high, but this time with the GH, so like the word like high up, right? If we call it on that, what this is going to return to us is actually just high, right? So HI, because that is that's quite literally the longest prefix of this word HIGH that exists in our trie. Okay, cool. So with that in mind, let's go back to the problem and see what we can do. So just like thinking generally, maybe not in terms of algorithmic stuff yet or anything, but just when you're sitting down and you're about to do a word search, maybe when you were younger, you did word searches in school and stuff. How would you go about it, right? For me, what I would do when I'm trying to solve a word search is I would, start looking at each letter, right, one by one, and look in all the different directions, right? So I would first look in the east direction, then the southeast, and the south, and the southwest, and then the west, and then northwest, and finally north, right? And I would look in all those 8 directions and make sure that, and sort of check if there's any of the target words, any of these guys, are in any of those directions from that letter, right? So I'd look at the H and see, is there a word there? No. I'd look here. Oh, there's Henry, right? So I can cross off Henry off my list. And then I'd move on to the other directions, and I'd go to maybe G, right? And I'd say from G, oh, there's a word right here, George. Nice. I check this direction, I check this direction, I check this direction, so on and so forth, until I've sort of exhausted all the possibilities. And obviously, you might do some optimizations. You might say, more words start with S, so maybe I'll look at the S's first. Or I'm specifically looking for Ethan, so I'm going to look at all the E's right now, something like that. But the general point is that one way to solve a word search is just simply to explore each and every letter in each direction. And if we think about it a little more, we can actually use a trie to implement exactly this, right? So the way that this algorithm is going to work is we're going to have a trie t. And into this trie t, what we're going to do is we're going to add all of our words, right? So all n of our sort of names that we're looking for. So all these guys are circled over here, right? And once we add them in, we're going to have a trie that resembles the thing down here, right? It's going to sort of store all the prefixes or sort of all the branches of words that might occur, right? So since we have like Soham and Sarah in our word set, we'll have like a Soham branch and another Sarah branch. And maybe if we had like a Sam, we would have a Sam branch over here too, something like that, right? The point is, we're going to make basically a trie that has all these words, okay? Cool. So once we do that, what we can do is we can do exactly what I was saying, which is we start at the first letter and look first in the southeast direction, or sorry, in the east direction, right? And what we're going to do is we're going to take that entire string. So for us, it's going to be H and the word George. So basically that entire first row. And we're going to pass this into LPO, right? So we're basically going to call LPO on H George for our tree, or for our trie, sorry. And if our trie, so if the call to LPO returns something that's not null, so it returns like an actual word, whatever this may be in here, that means that we've actually found a word. And we'll take a look at why in a second, right? So right now, H George is not going to return anything, right? So because there's no sort of string in our trie that has a prefix HGE or anything beyond that, right? So that's fine. But maybe when we call, let's look at the southeast direction now, Henry HA, right? So we say LPO on Henry HA. This time what this is going to return is it's going to return Henry, right? Because Henry is the longest prefix that is inside of our trie, right? We have the word Henry in it, and it's the longest prefix of this Henry Ha string that we passed in. And what that means is that, okay, so now we found a word. So whenever LPO returns something that's not null, that means that we found one of the words that we're looking for, right? And what we can do at this point is we can just remove that word from our trie. So maybe this is better illustrated with a smaller example. So let's kind of just walk through the algorithm a little bit, okay? So first we've stored all of our, let's say we've stored, we're looking for all these words. This actual word search doesn't have like HI or help or any of that, but just assume it does, okay? This is like a small subsection of a larger word search. And so let's say we've inserted HI into our trie. We've inserted hey, we've inserted help, and we've inserted hello, right? And now we're looking for each of these words. So let's follow our algorithm and let's do the first step. So our first step is going to be to start at the top left corner, right? And look at the first sort of east direction, right? So HEYB. If we call LPO on HEYB, this is going to return hey, right? Because that is the longest prefix of HEYB that is within our trie. And at this point, what we're going to do is we're going to quote unquote remove hey from our trie. And what removing really means in a trie is because like words are dependent, or there's multiple words dependent on the same letters in a trie. Whenever we remove one word, all we do is remove the characters that are unique to that word from the trie. What I mean is that if we want to remove hey, then all we're going to remove is just the Y, right? Because HE are still used in numerous other words, so we can't remove that stuff. So now hey is gone from our trie, right? And so the next step in the algorithm, after we've sort of found a word, is to sort of just repeat, right? So now that we've explored this direction, we can say, okay, now we check this direction, then we check this direction, and then we check EYB, and then EXY, EDOF, and then EC. So we kind of just keep going down the line, checking all 8 directions, or potentially 8 directions of each letter, until our trie is empty, right? Because once our trie is empty, then we know that we found all the possible words, right? If our tries return hi, then we remove the I. If it returns, let's say hello, then we can remove the O and this L. And finally, if it returns help, then we have no more words left in our trie, right? So we can erase the whole thing. And since our trie is empty, we now know that our word search is complete, right? We found all the words. And yeah, that's sort of the general gist of the algorithm. It sort of works pretty like intuitively to how you would actually solve a word search in real life, which is actually a pretty good way to tackle a lot of these algorithms. Whenever you're faced with on an exam, a good way to think about it is just to forget all the code stuff, forget all the loops and iterations and runtime and all that, and just start by thinking about if you sat down and needed to write this out on paper, how would you go about solving this problem? That's usually a pretty good way to come up with some kind of algorithm, and then you can sort of optimize it later on as you go. Okay, and so the last thing I think is just to go over the runtime of this guy. So as I said in the beginning, we can do up to n work for each letter, right? Because that's our constraint, n cubed. So since we have n squared letters, we're going to be visiting n squared letters potentially, right? In the worst case, we'd be going to every single letter, and for every single letter, we'd be doing potentially up to 8 sort of calls to LPO, right? So since LPO is taking a string of length n, we're going to be doing basically potentially 8 times n. So this is the absolute worst case. Obviously, this is not the actual real case, because there's a lot of letters on the edges that only have like 3 or 4 directions and stuff like that. But if we're going to analyze the algorithm, we're going to look at the absolute worst case, even if it's not very feasible. What that basically boils down to is, is 8n cubed, which, we ignore the coefficients, which boils down to an n cubed algorithm, right? Because we're doing n work for each of the 8 directions for each of the n squared letters. And yeah, I think that's about it. So I hope that was a helpful video.